Next speaker is Sofia Contarini, talking about cosmology with voids.
There are no voids in my slides. So as you can guess from the title, I'm going to talk about our favorite topic, cosmic voids. But in this case, I'm going to focus on void number counts. And some of the other things that I will show you today are already been introduced yesterday by Slaja, Rosa, and Nestor. So I will probably go very fast on those parts. So when I talk about cosmic voids, I mean the large underdensities of our universe. Trying to find the pointer. Yes, that together with clusters and filaments and walls form the so-called cosmic web. And looking at the volume content of the universe, we found out that voids occupy the majority of it. But it's also interesting to see that if we look at the mass content, voids hold anyway a good part of the mass, so they're not completely empty, right? But this picture, of course, depends a lot on the void finder that we use, so the definition of voids that we want to assume. And these have been introduced yesterday, but just to mention, we have different categories of void finders. We have spherical void finders, like these two, that use spheres or ensemble of spheres embedding a fixed density contrast. We have the geometrical void finder like VID and Revolver that were introduced yesterday. And we have the dynamical void finders, that is what Simone will be talking about after me, so no spoilers. So in general, however, when we talk about voids, we refer to underdensities, so regions with a density contrast that is between -1 and something like 1. So in general, we could say that they are quite easy to model because we can use linear theory or multi-linear one. And another good thing about voids is that they have a negligible baryonic feedback on them. So again, they are in principle quite easy to model. This is not completely true, of course. But another thing that was mentioned yesterday is that since they have a low matter content over very large scales, they are also very sensitive to dark energy, massive neutrinos, and modified gravity models. You can see here an example of this. This paper is from Slaja. And I want to mention one last point, that is that voids, especially void counts, are usually complementary to overdensity-based probes. And you can see an example here where void counts are in blue, and the constraints on omega matter and sigma 8 are orthogonal to those obtained with the weak lensing and galaxy string. But let's assume for a moment that we have a catalog of voids. What can we do with them? We can compute different summary statistics. We have the void size function, that is what I will introduce later. That is just the number counts of voids as a function of their size. Then we have the void galaxy cross-correlation function, that is what Slaja introduced yesterday. We have void radial velocity profiles, void autocorrelation function, weak lensing, the cross-correlation with CMB that you can also see here. And this paper is from Andrzej. And we also have void ellipticity. So all these statistics have a model, and we have a way to measure them. And I'm currently writing a review about all these things that will, I hope, be ready in next week. So stay tuned, please. Okay, so let's focus now on the void size function. So for the void size function, we have a model that is developed with the same exclusion set formalism used for the halo counts. In particular, this model was developed in 2004 by Schett and van der Weijert, and analogously to halo counts, we have sigma of R. So in this case, R is the size of voids that is instead different from sigma of M, that is the mass of halos. And instead of the collapse threshold, we have another negative one, that is what we choose for the formation of voids. This model was then extended in 2013 by Jennings et al. That basically imposed the conservation of the volume occupied by voids from the transition from linearity to non-linearity, and this is called the volume conserving model, or VDN. According to this model, voids are defined as spherical, non-overlapping regions embedding a fixed density contrast. Density contrast that we have to fix in the model here. And you can see that this works pretty well. But it's also important to highlight the fact that in order to use this model, we need to prepare voids in a way that they are aligned to this definition here. So or we use a void finder that is preparing voids like that, or we use what it is called cleaning, that is basically a rescaling of our voids. So whatever void finder you use, you can prepare them for this kind of modeling. I want also to mention that this is what we use up to now, but now we have a promising alternative. That is what is written here. It is an exclusion set approach combined with peak theory, and it is very promising, and we are going to test now because maybe it's better and can be used to also model really small voids. But going on from this, the PDN is good to predict voids identified in real space and in the dark matter distribution. So in reality, we need to take into account the effect of biased tracers. We also need to include the effect of ratio space distortions that you see here, and also of geometrical distortions. So for the first two effects, my solution was just to like a simplistic rescaling of the threshold that we use for void identification by means of a function of the bias of the tracers plus two nuisance parameters that can be calibrated via MOX or just left free. For the last effect, we can use the Aldo-Paczynski effect that was introduced by Zladja yesterday, so I will just skip it, sorry. But the final model, including these three effects, is what I call the extended VDN. So now we are finally ready to apply this model to real data. In particular, my first choice was to use BOSS DR12. And in particular, BOSS features about 1 million spectroscopic galaxies in the range of between 0.2 to 0.7, covering 10,000 square degrees. And with these kind of catalogs, we were able to find about 6,000 watershed voids with PID. But then after applying the cleaning, in order to use the VDN, we end up with a few hundreds. You can see here a comparison between the voids found in a slice of BOSS and the symmetric one for the MOX Pachi MOX that I use to calibrate the VDN. So basically prepare a two-dimensional prior for C-slope and C-offset that are the two free parameters of the model. And I also used Pachi MOX to test a series of things that you can see here. So after that, finally, I was able to derive constraints with the void counts. So these are the constraints for a flat lambda CDM cosmology, assuming Planck 2018 as a fiducial one. And these are the priors that I used and so on. It is important to notice that for omega CDM, the prior is very large, and the same thing for H. But for all the others, I'm just considering prior that is basically 10 times the uncertainty of Planck, so it's not that big. So the final constraints are those that you can see here with omega DE and sigma 8 that are derived. These are not super good, I know, but I will show you now something good. But before doing that, I want to show you another representation of these contours that is instead using physical units, in particular small omegas and sigma 12. Sigma 12 is just like sigma 8, but computed on a physical scale of 12 megaparsecs. That helps the interpretation of sigma as amplitude of the matter fluctuations. So these are very similar, and there's nothing important to notice, but just the comparison that I'm going to show you after this. So thanks to Gigi, I don't need to introduce Euclid, so I will just mention that is a fantastic survey that is going to be ready soon with DR1, but what we are really interested with for voids is DR3, that will cover about 14,000 square degrees. With Euclid, the constraints that we are going to have, hopefully, are something like that. So in this case, we calibrated C-slope and C-offset with flagship maps that are the official maps for Euclid. And we also assumed the bias from these maps. With this assumption, the relative improvement on the omega, sigma 12 and H are those that you can see here. So about from 60 to 70%. That is already very good. But I also want to show you what could be the future with WST, that is the Wide Field Spectroscopic Telescope, that for the moment is funded for a 3-year concept study. But the idea, if ESO will approve this, is to have a 12-meter telescope with both MOS and IFU that will be ready hopefully for 2040. With WST, we will have a huge amount of spectroscopic galaxies covering a super wide range of redshift that you can also see here. Yes. So the area covered by WST could be 18,000 square degrees, and the number of voids that we expect to have is about 1 million, just for the lowest redshift part. So just considering redshift lower than 1.5. Again, after cleaning this will be reduced to about 15K. But the constraints with this kind of voids will be even better. Of course, we are talking about 2040. But the relative improvement with just these voids with respect to Euclid are of this kind here. So from 40 to 50%. And in this case, we assumed the same calibration used for Euclid and the same galaxy bias, but this is of course a oversimplification, but this is a good assumption for the moment. And that's all. This is my final slide. I just want to mention that these are golden era for voids, because as you can see from this plot here, the number of voids that we identified from both to WST is exponential growing number. And there is an important thing to underline, that from great void catalogs, we also have to have a great modeling for them. So it is important to develop a theory that is robust enough to keep the pace with this kind of numbers. And that's all from me. Thank you for your attention.
Yeah, that's all.
When you compare the BOSS data and Euclid's predictions,
Yes.
the redshift range was kind of absolutely different. So there was no overlap between. Does it make any problem, or how can it? BOSS was like 0.2,
0.7, and Euclid starts from 0.9. Yes. What do you mean problems? We are probably different.
Do you expect the same constraints or same results?
No, we didn't. Also because Euclid covers a wider area and the number density of galaxies. So basically, the number density of galaxies also gives us the minimum radius size that we can afford to model. So the number of voids for Euclid will be much greater. So it's not comparable, but it's also nice that they are probably different times of the universe. So basically, will be a combination that is maybe very powerful in terms of covariance. I hope so, at least. But yeah, we didn't expect a comparable thing, of course.
No more questions. Thanks that you considered it.